Take a moment to lie down. Allow your body to sink into the surface beneath you, and let your eyes gently close. Feel the subtle quiet around you and the soft rhythm of your own breathing. As you settle, allow yourself to drift toward a world invisible to the naked eye, a domain that is always present yet rarely contemplated, a realm beyond the familiar solidity of matter. What exists beyond the atom? This question invites us to journey inward, to explore layers of reality smaller than the particles we learn to call fundamental. In the beginning, atoms themselves were imagined as the ultimate building blocks of matter, indivisible and eternal. Early theories described them as simple spheres, imperceptible yet forming the infinite variety of the observable world. Gradually, the limits of this simplicity were challenged as experimentation revealed structures within the atom, subatomic intricacies that would redefine our understanding of matter. Within each atom lies a dense central core, the nucleus, composed of protons and neutrons, each carrying properties that dictate the atom's identity and stability. Surrounding this core is a cloud of electrons, constantly in motion, their precise positions governed not by deterministic paths, but by probabilities described through quantum mechanics. These electrons interact through electromagnetic forces, their energy levels quantized, existing in distinct orbitals that define chemical behavior. The spatial distribution of electrons creates the subtle scaffolding of molecular bonds, shaping the chemical complexity we observe in the world around us. The nucleus itself is a composite structure where protons and neutrons are bound together by one of nature's strongest forces, the strong nuclear force. This force operates over distances far smaller than the atom itself, mediated by gluons that act as carriers, transmitting the binding energy that holds the nucleus intact. Inside each proton and neutron, quarks, fundamental constituents of matter, remain perpetually bound in a dynamic, restless interplay, constantly exchanging gluons in a perpetual quantum dance. There are 6 types of quarks, known as flavors: up, down, strange, charm, top, and bottom. Each possesses a property called color charge, and the combination of quarks inside nucleons always achieves a balance, resulting in color neutrality. Beyond the nucleus and its electrons, the world of subatomic particles is governed by 4 fundamental forces. Electromagnetism, familiar in its everyday manifestations, controls the interactions between charged particles, shaping chemistry and light alike. The strong nuclear force binds quarks into protons and neutrons into nuclei, while the weak nuclear force governs processes like radioactive decay and neutrino interactions. Gravity, though dominant on cosmic scales, exerts almost imperceptible influence at these subatomic distances, yet its universal presence hints at connections between the minutiae of particles and the vastness of the universe. The framework that describes these particles and forces is known as the Standard Model of Particle Physics. Within it, matter is represented by fermions, quarks, and leptons, while forces are mediated by bosons, particles such as photons for electromagnetism, W and Z, bosons for the weak force, and gluons for the strong force. Each particle interacts with others according to precise rules, their behaviors measurable, predictable, yet infinitely intricate. Neutrinos, for instance, are exceptionally light. Neutral leptons that interact so weakly with matter that billions pass through each of us every second without notice, revealing a universe of subtle activity beyond immediate perception. Even in the seeming emptiness between particles, a restless activity persists. Quantum fluctuations ensure that virtual particles constantly appear and vanish, a transient presence that contributes to observable effects like the Casimir force. Space at this scale is not void, but a seething, energetic field where uncertainty and probability dictate behavior. High-energy experiments, such as those conducted in particle accelerators, recreate these conditions, allowing scientists to probe matter under extreme circumstances, observing phenomena that echo the earliest moments of the universe itself. These studies illuminate how matter behaves at extraordinary densities and temperatures. In collisions that mimic the birth of the universe, quark-gluon plasma emerges, a fluid of unbound quarks and gluons that existed microseconds after the Big Bang. From this primordial state, nucleons formed, giving rise to the first atoms and setting the stage for the emergence of complexity that would ultimately build stars, planets, and life. Understanding these processes bridges the smallest scales with the largest, showing that subatomic behavior underpins the very structure and evolution of the cosmos. At the heart of all this, the Higgs boson plays a subtle but crucial role. Its associated field interacts with fundamental particles, endowing them with mass, a property that defines how they move, interact, and assemble. Without the Higgs field, the universe would lack the scaffolding necessary for atoms, molecules, or structures of any kind. This discovery, achieved through experiments at the Large Hadron Collider, confirmed theoretical predictions and deepened our understanding of how matter, at its most fundamental level, acquires the properties we observe. Even as we uncover these layers, questions remain. The nature of dark matter, which exerts gravitational influence yet remains invisible to electromagnetic detection, challenges our understanding of matter. The origins and properties of neutrinos, the asymmetry between matter and antimatter, and the potential existence of new particles beyond the standard model, all hint at a deeper, still unseen layer of reality. Each experiment, each measurement, extends the reach of our curiosity into domains where the familiar laws of the macroscopic world give way to probabilistic quantum phenomena, endlessly subtle and intricate. As we delve deeper, the behavior of matter under extraordinary energies becomes apparent. Within particle accelerators, atomic nuclei are propelled to velocities approaching the speed of light and collided with immense precision. These interactions momentarily dissolve the familiar structure of matter, liberating quarks and gluons from their confinement and revealing a plasma reminiscent of the universe's first microseconds. In this searing environment, the strong force manifests in its purest form, dictating how these fundamental particles interact and recombine as the plasma cools and condenses into more stable structures. Observing this fleeting state provides a window into conditions that no naturally occurring environment on Earth could replicate. Yet it is precisely here that the earliest mechanisms of matter assembly become tangible. Energy and mass are intertwined in these collisions, as described by Einstein's equation, E equals mc squared. Minute amounts of energy can generate entirely new particles, appearing from the vacuum in accordance with quantum field theory. Exotic forms of matter, such as strange quarks and heavy mesons, emerge temporarily, their lifespans measured in fractions of a second before decaying into more familiar particles. Each decay pathway, each energy distribution, carries information about the forces shaping these subatomic interactions, offering empirical evidence that refines our theoretical frameworks. These results ripple outward, connecting laboratory-scale events with the fundamental structure of the universe. Even in the apparent stillness of space, high-energy phenomena unfold. Cosmic rays, originating from distant supernovae and active galactic nuclei, collide with atoms in Earth's atmosphere, producing cascades of secondary particles that mirror, in miniature, the processes observed in accelerators. Neutrinos generated in these collisions traverse planets unimpeded, while photons and muons illuminate the energy transformations occurring across vast distances. The subatomic realm is thus not confined to laboratories. It exists interwoven with the cosmos, demonstrating that the smallest constituents of matter are also participants in the grandest of cosmic events. Within stars, subatomic interactions are equally critical. Hydrogen nuclei undergo fusion, combining to form helium through processes mediated by the weak force. Neutrinos escape nearly instantaneously, carrying away energy and providing a direct measure of these nuclear reactions. Fusion releases photons, whose journey from the core to the stellar surface spans thousands of years, yet ultimately manifests as the light that bathes planets and sustains chemical processes on their surfaces. The energy produced in these reactions is governed entirely by subatomic mechanics, with the balance of forces ensuring both stability and the gradual transformation of matter into heavier elements through nucleosynthesis. The death of massive stars amplifies the extremes of subatomic behavior. In the implosion of a supernova, densities and pressures surpass anything found under normal conditions, compressing matter to forms such as neutron-rich cores. Neutrons, each a composite of quarks, are packed so closely that their properties are profoundly affected by the surrounding environment. The resulting neutron star is a natural laboratory, exhibiting interactions among degenerate matter that defy everyday intuition, where quantum mechanics and relativity converge to dictate the behavior of matter on scales both microscopic and macroscopic. Gravitational forces, normally negligible within atomic dimensions, play an essential role in these astronomical environments. They shape the equilibrium between opposing pressures and influence the distribution of mass in ways that feed back into nuclear interactions. Even at the subatomic level, the coupling of matter with the curvature of space-time has subtle but measurable consequences. High-precision observations of pulsars, whose rotations are governed by these extreme conditions, yield insight into the equation of state for ultra-dense matter, linking observational astronomy with the deepest questions of particle physics. Back on Earth, the pursuit of elusive phenomena continues. The Higgs field, while providing mass to particles, interacts with a quantum vacuum in complex ways, influencing the behavior of virtual particles that flicker into and out of existence. Antimatter, produced in controlled reactions, annihilates upon contact with ordinary matter, releasing energy according to precise quantum predictions. The imbalance between matter and antimatter in the universe remains one of the most pressing questions, suggesting that subtle asymmetries in subatomic interactions during the early universe led to the matter-dominated cosmos we observe today. Every discovery in this domain expands the depth of our comprehension. Dark matter, though not directly observed, exerts gravitational influence on galactic scales, implying that the standard constituents of atoms represent only a fraction of the universe's total content. Experiments in underground laboratories, shielded from cosmic interference, seek to detect the rare interactions of these particles with ordinary matter. Similarly, neutrino observatories, located beneath ice and rock, trace the trajectories of particles that barely interact, revealing a universe more intricate than the visible, luminous structures suggest. Through each of these observations, the narrative of matter beyond the atom unfolds. The subatomic world is a symphony of forces, fields, and particles, interrelated in ways that govern everything from the fusion in stellar cores to the formation of planets and the chemistry of life. Patterns emerge not from chaos, but from consistent principles encoded in quantum mechanics and field theory, manifesting as observable phenomena across time and space. Each layer of understanding builds upon the last, revealing a cohesive and profoundly ordered universe, even in realms that are invisible to the human senses. Even within the apparent emptiness of space, the fabric of reality hums with activity. Quantum fields permeate every point, invisible yet essential, and particles manifest as localized excitations within these fields. The electromagnetic field, extending infinitely, governs interactions between charged particles, while the strong nuclear field binds quarks tightly within protons and neutrons, sustaining the atomic nucleus against the natural repulsion of like charges. The weak nuclear field, subtler in its influence, dictates processes of transformation, such as beta decay, allowing one type of particle to change into another, a mechanism fundamental to the evolution of matter in stars and the early universe. Virtual particles continuously emerge from these fields, a phenomenon predicted by quantum mechanics and confirmed through experimental observation. They appear for fleeting instants, carrying momentum and energy, and then vanish, yet their effects are tangible, influencing forces measured between objects in precisely controlled conditions. Casimir forces, vacuum polarization, and shifts in atomic energy levels all testify to this restless activity. The vacuum is thus not empty, but a dynamic stage upon which the smallest constituents of reality play out their interactions, imperceptible directly, yet integral to the structure of the universe. Experimental science has opened windows into this domain, providing tools to measure and manipulate subatomic processes. Particle accelerators propel atoms and subatomic particles to velocities approaching light speed, enabling collisions that release previously hidden forms of matter. Detectors surrounding these collisions track particle trajectories, energy distributions, and decay pathways, translating imperceptible interactions into measurable data. Each collision becomes a story, a transient event revealing patterns of behavior among the fundamental components of matter, and collectively, these results deepen our understanding of the forces that govern the cosmos. In these high-energy environments, previously theoretical predictions gain empirical footing. The Higgs boson, whose field imparts mass to other particles, emerges under precisely orchestrated conditions, its presence confirmed through careful analysis of decay products. The properties of neutrinos, once thought negligible, reveal subtle behaviors such as oscillation, transitioning between different flavors as they traverse vast distances. Such discoveries underscore that even the most elusive and ephemeral phenomena exert profound influence over the architecture of matter and the dynamics of the universe. Subatomic processes are not confined to laboratories. In the cores of stars, the same principles dictate energy generation through nuclear fusion. Hydrogen nuclei collide, overcoming electromagnetic repulsion with sufficient velocity to allow the strong nuclear force to bind them into helium. This reaction releases energy in the form of photons and neutrinos, sustaining the light and warmth that radiate outward across vast distances. These interactions, determined entirely by subatomic laws, orchestrate the chemical evolution of galaxies and the formation of heavier elements essential for planetary systems and the chemistry of life. As stars exhaust their fuel, conditions for extreme matter arise. Densities increase dramatically during supernova collapse, producing neutron-rich remnants where matter exists in degenerate forms. Neutrons, themselves composed of quarks bound by gluons, are compressed to extraordinary proximity, demonstrating interactions under pressures unattainable elsewhere. The behavior of such dense matter reflects an intricate balance between quantum principles and gravitational forces, merging scales of subatomic physics with the structure of celestial objects. Observations of pulsars, rotating neutron stars emitting periodic radiation, provide indirect measurements of these conditions, linking the minute to the cosmic. Even subtler phenomena capture attention. Dark matter, while not directly observable via electromagnetic interactions, reveals its presence through gravitational effects on galaxies and clusters. Experiments attempt to detect rare interactions with ordinary matter, while observatories measure cosmic signals that might hint at its composition. Similarly, dark energy, manifest in the accelerating expansion of the universe, influences the large-scale structure in ways that remain only partially understood. These enigmas underscore that the tangible particles and forces we study constitute only a portion of a broader, more intricate framework in which matter and energy coexist. The journey through the subatomic realm continues inward. Quarks within protons and neutrons experience confinement, a phenomenon where attempting to isolate a single quark results in the creation of additional quark-antiquark pairs, maintaining color neutrality. Gluons, themselves massless, yet carriers of the strong force, mediate these interactions in complex patterns, forming a dynamic internal structure that challenges direct observation. Lattice quantum chromodynamics, a computational approach, simulates these interactions, offering insight into particle masses, magnetic moments, and decay rates, revealing a constantly evolving internal landscape even within the smallest building blocks of matter. These processes, though occurring at incomprehensibly small scales, ripple outward, shaping atomic stability, chemical reactions, and ultimately the macroscopic structures we experience daily. Every molecule, every crystal, and every planetary formation is governed by these underlying subatomic principles. Understanding the world beyond atoms is not an abstraction. It is a recognition that all observable phenomena are emergent properties of interactions at scales invisible to human senses, yet precisely governed by natural laws, measured and understood through persistent observation and theoretical refinement. In this continuous exploration, the role of energy becomes apparent not only as a driver of motion, but as a medium through which matter manifests and transforms. Electromagnetic radiation, neutrinos, kinetic energy, and binding energy constitute different expressions of the same underlying principles. Each particle interaction Each quantum fluctuation represents a conversion or redistribution of energy, obeying conservation laws that maintain consistency across scales. These rules, though abstract, are observable in the laboratory and in cosmic phenomena alike, reinforcing the interconnectedness of the subatomic with the universal. Among the most subtle inhabitants of the subatomic world are neutrinos, particles so light and elusive that trillions pass through the human body every second without leaving a trace. They are born in nuclear reactions, within stars, in radioactive decay, and during cataclysmic cosmic events, journeying across vast stretches of space almost entirely unimpeded. Despite their near invisibility, neutrinos carry critical information about processes that cannot be observed directly, acting as messengers from the cores of stars and from the earliest moments of the universe. Their oscillations between flavors, electron, muon, and tau demonstrate that even the smallest particles have complex, dynamic identities, governed by subtle quantum laws that allow them to shift properties over distances and time. The vacuum itself, often imagined as empty, teems with possibilities. Quantum field theory describes it as a sea of fluctuating energy, where particle-antiparticle pairs spontaneously emerge and annihilate, and fields ripple with ephemeral excitations. These fluctuations influence measurable phenomena, including the energy levels of electrons bound to nuclei and forces between closely spaced objects. Even without matter present, the vacuum has structure, a latent potential that shapes the properties of particles and the behavior of forces, providing a silent stage upon which the drama of the subatomic unfolds. In laboratories, this structure is probed through precision measurements and high-energy collisions. Detectors track the passage of charged particles, revealing trajectories that encode momentum, mass, and decay patterns. Scintillators, calorimeters, and drift chambers translate invisible interactions into tangible data, while superconducting magnets steer particles along paths where their interactions can be analyzed. The insights gained extend far beyond the immediate experiments. They refine theoretical models, test the predictions of the standard model, and occasionally reveal phenomena that require entirely new frameworks to describe. High-energy experiments illuminate the transient states of matter that existed moments after the universe's inception. Collisions at the energy frontier create conditions in which quarks and gluons are no longer confined within protons and neutrons, forming a quark-gluon plasma. In this liquid-like medium, particles interact freely, exhibiting collective behavior that mirrors the first microseconds of cosmic history. As the plasma cools, quarks and gluons recombine into hadrons, following precise statistical distributions predicted by quantum chromodynamics. Studying these processes allows scientists to connect the properties of the smallest constituents with the evolution of the universe, tracing the chain from quarks to atoms to stars, and eventually to the chemical diversity essential for life. Exotic particles emerge in these extreme conditions, including mesons composed of quark-antiquark pairs and baryons containing heavier quark flavors like charm and bottom. Their brief existence provides a laboratory for observing the strong force in action, the mechanism by which quarks remain bound within larger structures. Each decay, each transformation, reveals the interplay between conservation laws, symmetry principles, and force interactions. Even as these particles vanish almost instantaneously, their fleeting presence leaves detectable traces, offering a window into behaviors inaccessible at lower energies. The relationship between mass and energy becomes palpable in these environments. Small amounts of kinetic energy convert into particle mass during high-energy collisions, illustrating the profound interconnection articulated in Einstein's famous relation. Conversely, particle annihilation converts mass back into energy, demonstrating the reversibility inherent in fundamental processes. These conversions, governed by immutable conservation laws, underscore the symmetry and consistency underlying subatomic interactions, revealing a universe that is both dynamic and ordered, intricate yet comprehensible through careful observation. Matter's arrangement is not merely a result of forces within individual particles, but emerges from collective behavior. In atomic nuclei, protons and neutrons arrange themselves according to energy considerations and the Pauli exclusion principle, creating patterns of stability and instability that dictate the types of atoms that can exist. Nuclear shells, magic numbers, and binding energies govern which isotopes are long-lived and which decay rapidly, shaping the chemical elements that compose planets, atmospheres, and living organisms. Understanding these arrangements bridges quantum mechanics with the observable chemistry of the world, demonstrating that even the smallest subatomic distinctions resonate through the macroscopic realm. As we consider the cosmos, it becomes evident that the world beyond atoms is intimately connected with large-scale structures. Cosmic rays bombard Earth continuously, producing showers of secondary particles that illustrate interactions occurring millions of light-years away. Neutrinos from distant supernovae pass unimpeded through planets, and gravitational lensing reveals the presence of unseen mass influencing the trajectories of light. These phenomena connect the minutiae of particle physics with the vast architecture of the universe, demonstrating that knowledge of subatomic behavior is not an abstraction, but a key to understanding cosmic evolution and the forces shaping all matter. Even at the level of fundamental forces, patterns emerge that suggest underlying unity. Electromagnetic and weak interactions converge in the electroweak framework, a theoretical synthesis confirmed through particle collisions and precision measurements. The strong force exhibits confinement and asymptotic freedom, revealing complex relationships between energy scales and interaction strength. Gravity, though weak on the scale of particles, permeates all space, suggesting that even at the deepest levels, matter is never isolated from the broader context of the universe. These forces collectively orchestrate the behavior of matter, establishing consistent principles from quarks to galaxies, an unbroken thread linking the infinitesimal with the infinite. The quest to understand matter beyond atoms extends into realms not yet fully illuminated. Dark matter, an invisible component of the universe, exerts gravitational influence that shapes galaxies, yet eludes direct detection. Researchers construct sensitive experiments deep underground, shielded from cosmic interference, in the hope of observing the rare interactions of hypothetical dark matter particles with ordinary matter. These searches involve cryogenic detectors, liquid noble gases, and highly sensitive photodetectors, each designed to capture the faintest hint of a passing particle. Though results remain tentative, the meticulous design and precision measurement reflect the persistent, deliberate nature of scientific exploration, a patient probing of the universe's hidden scaffolding. Parallel investigations explore the Higgs field with ever greater detail. The field itself is omnipresent, an invisible lattice that interacts with elementary particles to impart mass. The discovery of the Higgs boson at the Large Hadron Collider confirmed its existence, but subtler properties remain under scrutiny. Precision measurements examine how the Higgs couples to different particles, testing the limits of the standard model and seeking potential deviations that could reveal new physics. Understanding this field is fundamental, for mass defines inertia, gravitational interaction, and the formation of stable structures from atoms to planetary systems. Symmetry plays a central role in the organization of the subatomic world. Charge, parity, and time symmetries govern how particles behave and transform. Violations of these symmetries, observed in certain decays, have profound implications for the universe's evolution, including the predominance of matter over antimatter. Each measurement of symmetry and its exceptions reveals deeper layers of order and constraint, demonstrating that even at scales far smaller than the eye can perceive, the universe is governed by consistent, intricate principles. Particles and forces interact in networks of astonishing complexity. Quarks interact via gluons within protons and neutrons. Electrons occupy orbitals around nuclei, dictated by electromagnetic forces, and neutrinos pass through matter almost unaffected. Each type of particle carries distinct properties, mass, charge, spin, that dictate interaction possibilities and probabilities. Understanding these properties allows scientists to predict behavior in natural processes and to engineer experiments that illuminate phenomena otherwise inaccessible. Every interaction, no matter how transient, is a reflection of underlying laws that extend from the quantum level to macroscopic consequence. Advanced observational techniques continue to reveal connections between the subatomic and the cosmic. Neutrino observatories, buried beneath ice or rock track elusive particles originating from distant stars, supernovae, or even the remnants of the Big Bang. Particle accelerators recreate high-energy environments that approximate those conditions, allowing direct examination of processes that shaped the early universe. Data from these sources interlock, forming a coherent picture in which subatomic physics explains patterns observed across astronomical scales, from the formation of light elements to the structure of galaxy clusters. Even the void between particles is rich with implication. Quantum fluctuations give rise to momentary particle-antiparticle pairs, affecting the energy distribution within atomic systems and influencing forces that act across tiny distances. Vacuum polarization, the slight modification of a field due to these ephemeral particles, alters measurable quantities, confirming that emptiness is never truly empty. These effects, though subtle, are indispensable for precise calculations of particle behavior, contributing to technologies that rely on quantum electrodynamics and informing our understanding of the universe's earliest moments. Interactions among particles also dictate the life cycles of stars. Fusion within stellar cores converts mass to energy, releasing photons that gradually migrate outward, illuminating planets and sustaining chemical processes necessary for life. Neutrinos escape almost immediately, offering a direct, unfiltered view of reactions at the heart of the star. The elements produced through successive fusion cycles, carbon, oxygen, iron, provide the raw material for planets, atmospheres, and biological molecules. Each step in this process is governed by the interplay of subatomic forces, a precise choreography invisible to the naked eye, but fundamental to cosmic evolution. In extreme astrophysical environments, subatomic processes reveal their versatility. In neutron stars, the densities compress matter into nearly pure neutron configurations, and the strong force dictates the stability and arrangement of quarks within these neutrons. Magnetic fields, rotation, and gravitational forces combine to shape the behavior of these remnants, producing emissions detectable across vast distances. The observations of pulsars with rhythmic radiation and predictable rotations provide empirical evidence for the behavior of matter under conditions unattainable on Earth, demonstrating that subatomic interactions govern phenomena on both microscopic and astronomical scales. Even as new particles are hypothesized, searches for rare decays, sterile neutrinos, and potential dark sector constituents continue to expand the boundaries of knowledge. Precision measurements challenge existing models, occasionally suggesting phenomena beyond the standard model. Each incremental discovery contributes to a detailed mosaic, a picture of matter that is ever more intricate yet coherent, where every particle, every interaction, every subtle field effect forms part of an interconnected system spanning the universe. Through it all, the principles that govern the world beyond atoms reveal a universe of elegance and subtlety. Nothing is static. Forces and particles are engaged in a constant, dynamic exchange. Yet this activity adheres to consistent laws that maintain the structure of matter and the evolution of systems over time. The smallest constituents, invisible and ephemeral, underpin everything from the glow of distant stars to the solidity of the ground beneath our feet. Observing, measuring, and understanding these interactions allows us to perceive the quiet, intricate order that sustains the cosmos. Within the intricate layers of matter, quarks exhibit behaviors that are both predictable and subtly dynamic. Bound together by gluons, they never exist in isolation, yet their collective configurations define the properties of protons and neutrons. Each quark's spin, mass, and color charge combine with others in ways that obey strict quantum rules, resulting in emergent properties such as magnetic moments and decay probabilities. The interplay among quarks, mediated by gluon exchange, demonstrates that even within the smallest constituents, complexity arises from simple, consistent interactions, producing particles that are stable enough to form atomic nuclei, yet dynamic enough to participate in the universe's ongoing processes. Neutrinos continue to captivate researchers due to their ghostly nature. Produced abundantly in nuclear reactions, these particles traverse the cosmos without obstruction, providing glimpses into environments otherwise inaccessible. Solar neutrinos offer insight into fusion reactions in stellar cores, while supernova neutrinos reveal the violent collapse of massive stars. Neutrino oscillation, the gradual transformation between flavors, illustrates that mass and identity in the subatomic realm are not fixed but probabilistic, governed by interactions with the vacuum and subtle quantum effects. Each detection contributes to a larger understanding of the fundamental properties of matter and the forces acting upon it. In laboratories, experimental physicists recreate environments where particles reveal behaviors hidden in natural settings. Accelerators propel particles to near light speeds, and collisions unleash energy sufficient to manifest particles not normally observed. These fleeting states, existing for fractions of a second, allows scientists to study the strong and weak nuclear forces directly. Observations of rare decays, anomalous energy distributions, and particle lifetimes refine theoretical models and sometimes suggest phenomena that extend beyond the current understanding. Every experiment becomes a dialogue between prediction and observation, mapping the contours of a domain invisible yet profoundly consequential. Even empty space is suffused with subtle activity. Quantum fluctuations imbue the vacuum with temporary particle-antiparticle pairs, influencing measurable forces and energy levels in matter. The Casimir effect, a tangible consequence of these fluctuations, demonstrates that vacuum energy produces measurable pressure, subtly guiding the behavior of macroscopic objects at nanoscopic distances. These effects underscore that nothing in the subatomic realm exists in isolation. Fields, particles, and interactions are woven together into a continuum that defines reality at every scale. The behavior of matter under extreme conditions offers additional insight. Inside neutron stars, the density forces neutrons into arrangements that push the limits of known physics. Quarks within neutrons experience intense pressure, influencing the overall equation of state of the star. Magnetic fields, extreme rotation, and gravitational gradients interact with these dense forms of matter, producing phenomena such as pulsar timing and gravitational wave emission. Observations of these objects provide natural laboratories for testing quantum chromodynamics, general relativity, and nuclear physics under conditions impossible to reproduce terrestrially. High-energy particle collisions on Earth mirror these cosmic extremes. When nuclei collide at velocities approaching light speed, quarks and gluons can temporarily exist in a liberated fluid-like state known as quark-gluon plasma. Its behavior, including viscosity, flow, and thermalization, provides insight into the universe's first microseconds. As the plasma cools, particles recombine into hadrons, reflecting patterns predicted by theoretical models. These experiments illuminate the evolution of matter from primordial chaos to the ordered atomic structures that underpin chemistry and biology, linking the smallest scales to the emergence of complexity across the cosmos. The Higgs field remains central to understanding mass and stability. Its interaction with particles defines inertia, which in turn governs motion under applied forces and the formation of stable structures. Precision measurements of Higgs couplings inform the Standard Model, while small deviations may hint at physics beyond the current framework. Through the Higgs mechanism, mass becomes more than an abstract property. It is the factor that allows matter to clump, atoms to form, and stars and planets to emerge, establishing the foundation upon which observable reality rests. Dark matter and dark energy provide further context for the unseen forces shaping the universe. Although invisible to direct observation, dark matter's gravitational pull dictates the motion of stars within galaxies, while dark energy drives the accelerating expansion of the cosmos. Experiments in deep underground facilities and satellite-based observatories search for signatures of these elusive components, combining theory with precise measurement. Even if their direct properties remain undetected, the effects of these entities demonstrate that the subatomic realm extends into phenomena on the larger scales, linking the imperceptible with the cosmic tapestry. Collectively, these explorations reveal that the subatomic world is far from inert. Particles emerge, interact, and decay in a continuous, regulated flux, orchestrated by the fundamental forces. Quantum fields provide the scaffolding upon which this activity occurs, and symmetry principles dictate the allowable interactions and transformations. The results of these processes resonate outward, governing atomic structure, chemical bonding, stellar evolution, and the formation of galaxies. From the fleeting life of a meson to the steady glow of a distant star, the same underlying rules persist, manifesting in forms both ephemeral and enduring. Through this lens, the universe beyond atoms emerges as an intricate continuum, a delicate balance of forces, energy, and probability. Each particle interaction, each quantum fluctuation, and each field excitation contributes to a vast, interconnected structure. The microcosm and the macrocosm are inseparable, bound by the principles that govern matter itself. Observing these patterns cultivates an appreciation for the elegance, subtlety, and order that pervades every scale of existence, a silent testament to the depth and richness of the universe hidden within and beyond the atom. The pursuit of understanding matter beyond atoms has driven increasingly sophisticated experimental techniques. Detectors spanning kilometers of underground tunnels and massive arrays of sensors in ice or water capture fleeting traces of subatomic interactions. Cherenkov radiation, the SAR, faint light emitted when charged particles traverse these media, faster than light travels through the medium, illuminates the passage of neutrinos that would otherwise remain undetectable. Time-of-flight measurements, energy deposition analysis, and trajectory reconstruction transform invisible events into quantifiable data, revealing subtle processes that govern the universe at its most fundamental level. Symmetry underlies much of this subatomic architecture. Conserved quantities, such as electric charge, baryon number, and lepton number, dictate what transformations can occur and which cannot. Violations of expected symmetries, such as those observed in certain meson decays, provide insight into the predominance of matter over antimatter. These asymmetries, though minute, have cosmic consequences, shaping the abundance of elements and the composition of the universe itself. Understanding symmetry and its exceptions is essential for connecting microphysical interactions with the evolution of the cosmos. Even ephemeral particles illuminate deeper structures. Muons, heavier cousins of the electron, penetrate matter with relative ease, allowing their behavior to be tracked over meters of detector material. Their decay patterns, interactions, and magnetic moments offer stringent tests for theoretical predictions. Similarly, tau particles, unstable and short-lived, provide windows into weak interactions and flavor physics, revealing how subatomic processes conform to and occasionally challenge established models. Each particle, from the most stable to the most transient, contributes to a cumulative understanding of the fundamental scaffolding of matter. The interplay between quantum mechanics and relativity becomes essential when considering high-energy phenomena. Particles accelerated to near-light speeds experience relativistic effects, altering mass and energy relationships in measurable ways. Collisions at these velocities produce new particles according to the available energy, illustrating the equivalence of mass and energy in a tangible manner. Observing these outcomes allows physicists to test predictions with extraordinary precision, confirming the consistency of quantum field theory and providing insight into processes that govern the early universe. Exotic states of matter such as strange matter and hypernuclei, emerge under extreme conditions in both laboratories and astrophysical environments. Strange quarks, normally confined within protons and neutrons, can form bound states in high-energy collisions, revealing behaviors that illuminate the strong force. Hypernuclei, in which one or more nucleons contain a strange quark, provide experimental opportunities to test theoretical models and explore interactions that do not occur naturally under normal conditions. These investigations expand the boundaries of known matter and offer glimpses into possibilities that extend beyond familiar atomic structures. Particle accelerators not only probe the composition of matter, but also reproduce conditions reminiscent of the first moments after the Big Bang. In these high-energy collisions, quark-gluon plasma emerges, a liquid-like state where quarks and gluons move freely, unbound by the confines of nucleons. Observing its formation, flow, and cooling informs our understanding of how matter transitioned from a chaotic primordial state into the ordered nuclei that later combined to form atoms. Each experiment provides a precise temporal snapshot of a fleeting moment in cosmic history, linking the infinitesimal with the monumental. In parallel, theoretical frameworks guide and interpret these observations. Lattice quantum chromodynamics uses computational grids to simulate quark interactions, while effective field theories simplify complex dynamics at larger scales. These models bridge the gap between raw data and underlying principles, allowing scientists to predict particle properties, decay rates, and interaction strengths with remarkable accuracy. Together, experiment and theory converge to create a cohesive map of the subatomic world, one that continuously evolves as new discoveries refine or expand existing knowledge. Neutrinos remain among the most enigmatic probes of these processes. Their minimal interactions make them challenging to detect, yet they carry unaltered information from regions otherwise inaccessible, such as the dense cores of collapsing stars or the earliest seconds of the universe. Large-scale detectors, buried deep to shield from background noise, capture their passage, and careful analysis of timing, energy, and direction enables reconstruction of distant astrophysical events. In this way, particles that barely interact provide a unique lens into both the mechanics of subatomic matter and the dynamics of cosmic evolution. The interrelation of forces, particles, and fields emerges as a persistent theme. The strong force confines quarks. The weak force allows transformation and decay. Electromagnetism shapes atomic and molecular behavior, and gravity binds macroscopic structures. Though vastly different in strength and scale, these forces operate in concert, producing the universe's remarkable coherence. Even subtle variations in these interactions could drastically alter the formation of atoms, stars, and galaxies, underscoring the delicate balance that permits the complexity observed at all scales. Observing the subatomic realm invites reflection on the intimate connection between the imperceptible and the visible. Every photon emitted by a star, every chemical reaction in a planet's atmosphere, every structural arrangement of matter ultimately traces its origin to the properties and interactions of subatomic particles. The elegance of these processes, unfolding continuously without conscious design, reveals a universe of remarkable order, hidden within layers smaller than atoms, yet foundational to every observable phenomenon. Within the tapestry of the subatomic world, particle lifetimes offer a delicate measure of stability and transformation. Unstable particles, such as mesons and heavier baryons, exist only briefly before decaying into lighter constituents. Each decay pathway adheres to strict conservation laws, conserving energy, momentum, charge, and other quantum numbers. Observing these processes reveals the hierarchy of forces, the relative strengths and probabilities governing interactions, and the subtle asymmetries that differentiate matter from antimatter. The fleeting existence of these particles serves as a testament to the dynamic, ever-changing nature of the quantum realm. Decay chains extend this narrative, tracing the sequence from high-energy progenitors to stable, long-lived products. A single high-energy collision can produce a cascade of transformations, each step governed by the same universal principles. The order and timing of these transitions are not arbitrary. They encode information about interaction strengths, particle couplings, and the underlying symmetries of nature. By analyzing decay sequences, physicists reconstruct the architecture of subatomic interactions, revealing patterns invisible to the unaided eye, yet consistent across diverse experiments and energy scales. The study of rare and exotic processes further deepens understanding. Searches for neutrinoless double beta decay, proton decay, or anomalous transitions aim to uncover subtle deviations from established theory. Detecting such phenomena would illuminate new aspects of matter, potentially pointing toward unifying frameworks that link the known forces or explain the abundance of matter over antimatter. Even in their absence, these experiments constrain theoretical models with extreme precision, refining our picture of the subatomic world and delineating the boundaries within which it operates. Cosmic implications of subatomic behavior are profound. The distribution of elements, the formation of stars, and the dynamics of galaxies are all influenced by the outcomes of nuclear reactions and particle interactions. Supernovae, for instance, produce neutrinos and heavy elements that seed the interstellar medium. The decay of unstable isotopes contributes energy over extended periods, influencing star formation and planetary development. In this way, the minutiae of particle interactions ripple outward, shaping the architecture of the universe and the conditions that make planetary systems and life possible. The quantum vacuum continues to reveal unexpected subtlety. Fluctuations in fields generate ephemeral particle-antiparticle pairs, which influence forces between atoms and nuclei. These effects, though imperceptible in daily life, are measurable with precise instrumentation and critical to understanding fundamental constants and interactions. The vacuum is a reservoir of latent activity, a silent but persistent force shaping the properties of matter and the propagation of energy through space. Its influence reaches from subatomic calculations to cosmological phenomena, bridging scales in ways both subtle and profound. Even the geometry of space-time interweaves with subatomic processes. Gravitational fields influence particle trajectories, bending paths and shifting energy distributions in ways predicted by general relativity. In extreme environments, such as near black holes or within neutron stars, the curvature of space-time modifies interactions among densely packed particles, producing effects that are simultaneously quantum and relativistic. Studying these regions provides insight into the convergence of fundamental theories, testing the boundaries of current understanding and suggesting avenues for unified descriptions of matter and energy. Particle accelerators, despite their relatively small scale compared to the cosmos, simulate these extreme conditions with remarkable precision. Collisions recreate energies and densities akin to those of the early universe, enabling observation of transient states that reveal the behavior of quarks, gluons, and exotic particles. Each collision is a controlled experiment in creation and decay, offering insight into symmetries, coupling constants, and the mechanisms by which matter organizes itself. These experiments connect laboratory observation to the broader narrative of cosmic evolution, demonstrating that the principles governing the smallest scales are fundamental to the largest structures. Interactions within atomic nuclei continue to illuminate the balance of forces. Protons and neutrons are arranged in energy shells, exhibiting patterns of stability and decay that define the range of isotopes. The interplay of the strong force, electromagnetic repulsion, and quantum principles such as the Pauli exclusion principle dictates these arrangements. Observations of nuclear reactions, decay rates, and binding energies inform astrophysical models and underpin applications ranging from nuclear energy to medical imaging. Even the most subtle properties, spin alignments, parity characteristics, and energy thresholds, play a role in the emergent behavior of matter across scales. Neutrinos, once considered nearly inert, have become crucial probes of both particle physics and astrophysics. Their minimal interaction cross-section allows them to escape dense environments, carrying unaltered information from stellar cores and cataclysmic events. Observatories detect their arrival. An analysis of energy, timing, and direction reconstructs distant processes with remarkable fidelity. The study of neutrino oscillations, mass hierarchy, and potential sterile species deepens understanding of fundamental physics while illuminating the mechanisms behind stellar evolution and the early universe. From these observations emerges a coherent vision. The subatomic realm, though invisible, orchestrates the architecture of reality. Every particle, every interaction, every fluctuation contributes to a continuous, ordered process that shapes matter, energy, and the cosmos. Forces interweave with fields, symmetries constrain possibilities, and decay chains trace histories from the ephemeral to the enduring. Through careful measurement and persistent inquiry, humanity uncovers these patterns, revealing a universe whose complexity is mirrored in the precise, subtle, and dynamic world beyond atoms. Among the frontiers of subatomic exploration, the search for particles beyond the standard model stands as one of the most compelling pursuits. Hypothetical entities such as axions, sterile neutrinos, and supersymmetric partners have been proposed to address phenomena not fully explained by existing frameworks, including dark matter and the matter-antimatter imbalance. Experiments are designed with extraordinary sensitivity, employing cryogenic chambers, ultra-pure materials, and magnetic shielding to isolate potential signals from background noise. Even non-detection refines theoretical predictions, narrowing possibilities and deepening our comprehension of the subtle structures governing matter. The interactions of quarks in extreme conditions reveal further layers of complexity. High-energy collisions produce temporary states containing heavier flavors, charm, bottom, and even top quarks, whose decay sequences expose the dynamics of the strong and weak forces. Gluons mediate binding, exhibiting color confinement and asymptotic freedom. so that quarks behave as though free at extremely short distances, yet remain inseparable at larger scales. These phenomena, observed indirectly through decay products and collision patterns, demonstrate the richness of internal structure within protons, neutrons, and exotic hadrons, expanding the catalogue of known particle behavior. Energy and mass remain intimately entwined. In particle collisions, kinetic energy is converted into new particle mass, illustrating the direct manifestation of Einstein's principle. Conversely, particle annihilation transforms mass back into energy, as observed in positron-electron interactions or meson decay. These conversions are not abstract. They shape the outcomes of high-energy experiments, the production of cosmic rays, and the generation of light in stellar interiors. The constant interchange between energy and mass underlies the dynamic evolution of matter at every scale, connecting the imperceptible quantum domain with observable physical phenomena. Dark sector investigations extend this understanding to invisible components of the universe. Dark matter, inferred from galactic rotation curves, gravitational lensing, and large-scale structure, exerts influence without detectable electromagnetic interaction. Experiments in deep underground laboratories, employing scintillation detectors, cryogenic phonon sensors, and time projection chambers, search for rare interactions between dark matter candidates and ordinary nuclei. Dark energy, inferred from the accelerating expansion of the cosmos, remains even more enigmatic, yet its effect shapes the distribution and motion of galaxies over billions of years. These phenomena reveal that the subatomic world encompasses not only what is detectable, but also what remains hidden, guiding cosmic evolution in profound ways. Symmetry and its subtle violations continue to inform our understanding of fundamental processes. Charge parity, CP violation, observed in certain meson decays, indicates slight differences in behavior between matter and antimatter. These asymmetries, though minuscule, help explain why the universe is composed predominantly of matter. Observing such violations requires experiments of exceptional precision, tracking particle trajectories, decay products, and timing to reconstruct patterns consistent with theoretical predictions. These insights link microphysical behavior with cosmic-scale outcomes, illustrating the interconnectedness of fundamental laws. The vacuum's restless character is a constant presence. Fluctuating quantum fields give rise to ephemeral particle-antiparticle pairs, temporarily modifying the behavior of real particles and influencing measurable forces. Phenomena such as the Lamb shift and the Casimir effect provide tangible evidence of this underlying activity. In essence, the vacuum is not a void, but a dynamic arena in which particles are continually created and annihilated, shaping the energy landscape in which matter exists and interacts. Astrophysical events amplify subatomic processes to scales that can be observed across the universe. Supernova explosions produce neutrinos in enormous numbers, carrying energy and information from stellar cores that photons cannot escape. Cosmic rays, consisting of high-energy protons and nuclei, bombard planetary atmospheres, creating secondary particle showers detectable by ground-based observatories. The interaction of these cosmic travelers with interstellar magnetic fields and matter reveals the ongoing influence of subatomic physics on galactic and extragalactic phenomena, connecting the quantum world with large-scale structure. The study of nuclei continues to uncover subtleties in the organization of matter, binding energy nuclear spin, and parity determine stability and dictate decay patterns. Energy levels within the nucleus govern reaction probabilities in both laboratory and astrophysical settings. Nuclear reactions in stars convert lighter elements into heavier ones, releasing energy that sustains stellar luminosity. The precise balance of forces and energy within each nucleus ensures the ongoing synthesis of elements, influencing planetary composition, chemical diversity, and the raw materials necessary for life. Even in laboratory conditions, researchers create matter under conditions reminiscent of stellar interiors. Heavy ion collisions generate high temperatures and pressures, producing short-lived exotic nuclei and strange matter configurations. Observations of these transient states provide insight into the interactions of quarks and gluons beyond ordinary protons and neutrons. Data collected from these experiments inform models of neutron stars, supernovae, and the early universe, reinforcing the principle that the behavior of subatomic particles underlies the formation and evolution of cosmic structures. Through these investigations, it becomes increasingly evident that matter beyond atoms is an intricate dynamic system governed by consistent, measurable laws. Fields, forces, and particles interact continuously, producing phenomena that scale from the quantum to the cosmic. The behavior of the smallest constituents, though invisible, dictates the patterns and properties of all observable matter. Recognizing this interconnection cultivates an appreciation for the subtle elegance inherent in nature, where complexity arises from the simple, unbroken principles that govern every particle, every interaction, and every fluctuation across the universe. Quantum fields form the foundation upon which all subatomic phenomena unfold. Each particle corresponds to a specific field, a pervasive entity that stretches through all space. Excitations of these fields manifest as particles, with properties determined by the underlying mathematics of the field itself. Fluctuations, interactions, and propagations within these fields give rise to the forces that bind matter, mediate decay, and govern motion. In this view, particles are not isolated objects, but expressions of dynamic, continuous activity within a vast, interconnected network, where every vibration and interaction carries consequences that extend beyond the immediately observable. The unification of forces remains a guiding principle in understanding the subatomic realm. Electromagnetic and weak interactions merge under the electroweak framework, demonstrating that seemingly distinct forces are aspects of a single underlying interaction. The strong force governing quark confinement and gravity, acting over vast distances, remain separate in current models, yet efforts continue to formulate theories that encompass all four fundamental forces. The pursuit of such unification drives experimental design, theoretical development, and computational simulation, revealing the coherence and consistency underlying phenomena that, at first glance, appear disparate. Energy propagation at the subatomic scale is continuous and regulated. Particles transfer momentum through interactions mediated by force carriers, whether photons for electromagnetism, gluons for the strong force, or W and Z bosons for the weak force. These exchanges dictate particle trajectories, binding energies, and decay pathways. Even in the absence of direct collisions, virtual particles within quantum fields influence measurable properties, modifying forces and producing subtle effects that, when measured with precision, provide insight into the otherwise hidden structure of reality. Exotic matter continues to challenge understanding and expand theoretical boundaries. Strange quark-containing baryons, charm and bottom quarks, and transient mesons reveal the versatility and richness of particle interactions. Observing these rare configurations requires high-energy accelerators and sensitive detectors capable of resolving ephemeral states. Each discovery deepens the mapping of the subatomic landscape, showing that even within a seemingly constrained framework, matter exhibits a diversity of forms, behaviors, and interactions, all governed by consistent physical principles. Laboratory simulations often parallel astrophysical extremes. Heavy ion collisions recreate conditions analogous to stellar cores or the universe's earliest moments, producing quark-gluon plasma and exotic nuclei. The cooling, recombination, and decay of these states offer insights into the processes that form the first stable matter. Through careful measurement of energy distributions, decay patterns, and interaction rates, researchers reconstruct conditions that existed microseconds after the Big Bang, connecting terrestrial experiments to the universe's formative epochs. Neutrinos persist as subtle messengers from distant, otherwise opaque environments. Their weak interactions allow them to escape dense cores, traverse interstellar space, and reach detectors on Earth with minimal alteration. Analysis of neutrino flux, energy spectrum, and oscillation behavior informs both stellar physics and fundamental particle properties. In detecting and interpreting these particles, scientists probe conditions unreachable by other means, bridging the gap between inaccessible regions of space and our capacity for measurement and understanding. The interweaving of subatomic processes with cosmic structure is evident in element formation. Nuclear fusion in stars transforms hydrogen into helium and heavier elements, releasing energy that sustains luminosity. Supernovae distribute these elements into interstellar space, seeding future generations of stars and planets. Radioactive decay over extended periods contributes energy and influences planetary differentiation. In each case, the minutiae of particle interactions, fusion cross-sections, decay half-lives, and binding energies dictate outcomes that shape chemical composition, planetary formation, and the conditions for life. Even in the vacuum, the interplay of fields and fluctuations exerts influence. Virtual particle-antiparticle pairs briefly emerge, altering energy distributions and generating measurable effects such as the Lamb shift in hydrogen or the Casimir force between uncharged plates. These manifestations of vacuum activity reveal that space itself is a dynamic participant in the behavior of matter, a substrate through which forces operate and interactions propagate. Though imperceptible to the senses, the vacuum's role is essential, shaping the fundamental constants and parameters that define the observable universe. High-energy cosmic rays offer another bridge between subatomic and astronomical phenomena. Protons and heavier nuclei accelerated by distant astrophysical engines collide with planetary atmospheres, producing secondary particles and radiation that can be observed from Earth. These interactions provide empirical insight into particle physics under extreme conditions, while simultaneously offering data on the structure and dynamics of the cosmos. Through careful analysis, the behavior of subatomic constituents informs our understanding of phenomena spanning scales from nanometers to light years. Across these diverse phenomena, a unifying principle emerges. Subatomic processes operate under consistent laws, manifesting in complexity without contradiction. The motion of quarks, the oscillation of neutrinos, the decay of mesons, and the propagation of fields all adhere to predictable patterns defined by symmetry, conservation, and interaction strengths. From these microscopic interactions arises the architecture of matter, energy distribution, and cosmic evolution, demonstrating that even the smallest, most elusive particles are integral to the coherent order of the universe. Symmetry breaking emerges as a subtle yet profound influence within the subatomic world. While many interactions exhibit near-perfect symmetry, slight deviations introduce critical consequences. The breaking of electroweak symmetry through the Higgs mechanism grants mass to particles, allowing them to interact and aggregate into atoms and larger structures. Similarly, the observed asymmetry between matter and antimatter, manifested in rare meson decays and CP violation, underlies the predominance of matter in the universe. These small, precise deviations from ideal symmetry demonstrate that imperfection, rather than uniformity, often drives the evolution of complex structures. Precision measurements continue to probe the limits of theoretical models. Observations of magnetic moments, decay lifetimes, and scattering cross-sections allow scientists to test predictions to extraordinary accuracy. Even minuscule discrepancies between calculated and measured values can indicate new physics or refine existing understanding. High-resolution detectors, low-noise electronics, and carefully controlled experimental conditions enable these studies, revealing the exacting balance of forces that govern the stability and transformation of subatomic particles. The endeavor emphasizes that understanding the universe beyond atoms requires patience, meticulous methodology, and acute sensitivity to detail. Dark sector investigations remain an ongoing frontier. Candidate particles, such as axions or sterile neutrinos, may interact only weakly with ordinary matter, making them elusive yet essential to explaining cosmological phenomena. Gravitational effects provide indirect evidence, while direct detection experiments attempt to capture rare, scattering events. Even the absence of observed signals contributes to refining theoretical constraints, shaping the contours of what is possible within the subatomic framework. These efforts demonstrate the interplay between observation, inference, and theory in revealing aspects of reality that remain hidden from direct view. Particle interactions in novel environments continue to expand the scope of understanding. In dense astrophysical objects, quarks and leptons behave under pressures and temperatures far exceeding terrestrial conditions. Strange quark matter, hyperons, and other exotic states emerge transiently, providing insight into the strong force and the behavior of nuclear matter at its limits. Observations of neutron star mergers, pulsar timing, and gravitational wave signals reveal the macroscopic consequences of these microphysical interactions, illustrating that the laws governing the subatomic world manifest across scales in predictable and measurable ways. Quantum entanglement, once considered a theoretical curiosity, demonstrates that particles can exhibit correlations over vast distances. Entangled pairs maintain linked properties such that the measurement of one immediately influences the state of the other, a phenomenon verified repeatedly in laboratories with photons, electrons, and other particles. These correlations are not merely abstract. They underpin the foundations of quantum field theory, inform studies of decoherence, and inspire technologies such as quantum computing and secure communication. Entanglement exemplifies how subatomic principles challenge classical intuition while adhering to a coherent, mathematically describable framework. The transfer and propagation of energy at the subatomic scale shapes observable matter. Photons mediate electromagnetic interactions, gluons enforce quark confinement, and W and Z bosons govern weak processes such as beta decay. Even in the absence of material particles, virtual excitations within fields influence the behavior of systems, adjusting effective forces and energy landscapes. These dynamics, though imperceptible in everyday experience, dictate chemical reactivity, nuclear stability, and the emission of radiation across the electromagnetic spectrum. Energy, as it moves and transforms, maintains continuity from the quantum domain to macroscopic phenomena. Experimental observations increasingly bridge theory and cosmic scale. Heavy ion collisions reveal the properties of quark-gluon plasma. Neutrino detectors trace stellar interiors, and high-precision spectroscopy maps energy levels within atoms. Each measurement refines models of fundamental interactions, creating a feedback loop in which observation informs theory, which in turn predicts new phenomena. The iterative process strengthens understanding, gradually filling in the mosaic of the subatomic world and its influence on the universe at large. Even the smallest particles participate in processes that determine elemental abundances. Nuclear fusion in stars converts hydrogen to helium and heavier elements through chains of reactions governed by strong and weak forces. The resulting isotopic ratios, influenced by decay pathways, binding energies, and reaction cross-sections, shape the material available for planet formation and subsequent chemical evolution. The interplay of subatomic physics and stellar dynamics underscores the profound connectivity between microscopic interactions and the conditions necessary for planetary systems to develop. Vacuum fluctuations continue to illustrate the active nature of space itself. Temporarily arising particle-antiparticle pairs influence field strengths, modify effective potentials, and contribute to observable effects such as Lamb shifts. These fluctuations, while fleeting, are integral to the stability of atoms, the propagation of forces, and the precision of fundamental constants. Observing and quantifying these effects reveals that even empty space is a dynamic participant in the architecture of reality, a stage upon which particles and fields interact continuously. Through this intricate web of forces, interactions, and symmetries, the subatomic world asserts its influence across scales. Every particle, whether fleeting or stable, contributes to the ongoing organization of matter. Every field fluctuation, decay pathway, or energy transfer propagates consequences that ripple outward, shaping atoms, molecules, stars, and galaxies. In this continuous process, the universe beyond atoms emerges not as static or random, but as a dynamic, ordered system where the imperceptible orchestrates the observable, and where each interaction, however small, has meaning in the grand design of cosmic evolution. The interplay of subatomic forces manifests in subtle patterns that govern the stability of matter. Binding energies within nuclei arise from a balance between the strong force which holds quarks and nucleons together, and the electromagnetic repulsion between protons. Slight variations in these energies can alter the lifetimes of isotopes, the paths of nuclear reactions, and the synthesis of elements in stars. By studying these effects in detail, physicists discern the thresholds and constraints that enable the formation of complex atomic structures, the kind that assemble into molecules and ultimately compose the material world. Observations of particle interactions continue to reveal unexpected coherence within apparent randomness. High-energy experiments produce showers of particles that, while initially chaotic, conform statistically to precise distributions predicted by quantum chromodynamics and electroweak theory. Patterns emerge in the angular distributions, momentum transfer, and decay sequences, reflecting the underlying symmetry principles and conservation laws. Each experimental result, no matter how transient, contributes to a larger narrative, connecting fleeting subatomic events with enduring physical laws. Even ephemeral resonances illuminate deep properties of matter. Mesons and baryons, formed briefly in particle collisions, decay according to well-defined probabilities. Their lifetimes, spin alignments, and decay channels provide insight into coupling constants, internal quark arrangements, and the influence of virtual particles. These resonances act as windows into the internal structure of matter, demonstrating that even states that exist for billionths of a second carry significant information about the governing principles of the subatomic world. Cosmic rays offer a bridge between the minute and the immense. Protons and heavier nuclei, accelerated to near light speeds by distant astrophysical phenomena, collide with planetary atmospheres, generating secondary particles and showers detectable across large-scale observatories. Analysis of these events informs our understanding of high-energy particle interactions, the composition of the interstellar medium, and the propagation of energy across cosmic distances. In this way, the behavior of individual particles has consequences that extend from nanometer scales to intergalactic space. The study of quantum chromodynamics continues to refine understanding of the strong force. Quarks interact through the exchange of gluons, exhibiting confinement and asymptotic freedom that dictate how matter behaves at subnuclear distances. Lattice simulations, effective field theories, and scattering experiments provide complementary perspectives, allowing researchers to probe both static properties of hadrons and dynamic processes in high-energy collisions. Through these approaches, the richness of quark behavior, from spin alignment to flavor transitions, becomes increasingly clear. Exotic configurations such as tetraquarks and pentaquarks expand the known repertoire of subatomic structures. Though short-lived, these arrangements reveal how quarks can combine in ways that transcend conventional baryon or meson classifications. Each observation challenges theoretical models, prompting refinement and deeper exploration of binding mechanisms, color charge arrangements, and decay pathways. The diversity of these forms underscores that, even within strict rules, matter exhibits versatility and complexity, suggesting that the subatomic landscape is richer than previously imagined. Energy transfer at the quantum level dictates the behavior of fields and particles alike. Photons mediate electromagnetic interactions. W and Z bosons govern weak processes, and gluons enforce the strong interactions binding quarks. Virtual excitations continuously influence forces, modifying effective potentials and guiding the interactions of real particles. These exchanges, imperceptible to human senses, are measurable and repeatable, forming the operational backbone of chemistry, nuclear physics, and astrophysical processes. The flow of energy, though subtle, orchestrates the dance of matter across scales. Neutrino oscillations exemplify the nuanced behavior of subatomic particles. These transformations between flavors occur over measurable distances and times, influenced by mass differences and interactions with matter. Observing the oscillation patterns allows researchers to infer properties that are otherwise hidden, providing information on the mass hierarchy of neutrinos and contributing to broader cosmological models. The subtlety of these effects highlights the precision and sensitivity required to understand phenomena beyond direct perception. Within laboratories, heavy ion collisions mimic conditions found in the early universe. Quark-gluon plasma, liberated momentarily from confinement, flows as a near-perfect fluid, revealing the dynamics of the strong force under extreme energy density. Its cooling and recombination into hadrons mirrors the transition from primordial chaos to structured matter. By measuring energy flow, particle correlations, and thermalization patterns, physicists reconstruct the processes that shaped the formation of the first atomic nuclei, connecting microscopic events with the grand timeline of cosmic evolution. Across all scales, from the fleeting existence of resonances to the persistent effects of dark matter, the universe beyond atoms reveals continuous order and interaction. Every particle, every fluctuation, every force contributes to an intricate, interconnected system. Observing these phenomena cultivates an awareness of the elegant and consistent principles that govern matter, illustrating that the apparent complexity of the cosmos arises naturally from simple, universal rules. Subatomic behavior, though invisible, underlies every structure, every reaction, and every form of energy in the universe. Dark matter research continues to challenge our perception of the universe. Though invisible to electromagnetic detection, its gravitational influence shapes the rotation of galaxies, the formation of clusters, and the evolution of large-scale structure. Experiments designed to detect direct interactions employ ultra-sensitive detectors deep underground or in isolated cryogenic chambers. Any scattering event between a dark matter particle and ordinary matter, though exceedingly rare, would provide crucial insight into the nature of this enigmatic component. Until such events are observed, researchers rely on indirect evidence and precise cosmological measurements, constructing models that predict distribution, density, and interaction strengths of dark matter across cosmic time. The propagation of energy through subatomic interactions extends to the study of high-energy cosmic phenomena. When ultra-high-energy cosmic rays strike interstellar gas or planetary atmospheres, cascades of secondary particles unfold. Each collision follows the principles of quantum field theory, with probabilities dictated by cross-sections and conservation laws. Observing these cascades allows scientists to test particle physics under conditions unattainable in terrestrial accelerators. In turn, these observations inform models of astrophysical accelerators, magnetic field structures, and the propagation of matter and energy across vast interstellar distances. Subatomic particles reveal their intricacies in both isolation and ensemble. Single particle behavior, as in neutrino oscillations or muon decay, provides insight into intrinsic properties. Yet collective phenomena, such as quark-gluon plasma or coherent nuclear excitations, demonstrate emergent behaviors arising from the interaction of many constituents. These collective effects bridge the gap between individual particle physics and macroscopic observables, illustrating that understanding matter beyond atoms requires both micro and macro perspectives, where individual rules combine to produce complex, measurable outcomes. Theoretical frameworks continue to unify observations with predictions. Lattice quantum chromodynamics models quark interactions in discrete spacetime grids, providing numerical solutions to the dynamics of strong force confinement. Effective field theories simplify complex interactions for practical calculations, linking low-energy phenomena to fundamental couplings. These models are continuously refined by experimental results, forming a dynamic interplay between theory and observation. They allow physicists to predict particle masses, decay rates, and scattering probabilities with remarkable precision, demonstrating the predictive power of well-constructed mathematical frameworks. Even seemingly empty space plays an active role in subatomic processes. Vacuum fluctuations, the temporary appearance of particle-antiparticle pairs, influence the properties of atoms, contribute to measurable shifts in energy levels, and mediate forces between neutral objects. Though transient and invisible, these effects have cumulative consequences, shaping the behavior of matter and informing our understanding of fundamental constants. The vacuum is not a void, but a dynamic participant in the orchestration of subatomic phenomena, a stage upon which every interaction unfolds. Exotic nuclear states continue to expand the landscape of matter. Hypernuclei, where one or more nucleons contain a strange quark, and other unusual isotopes created in high-energy collisions, provide insight into strong force dynamics under atypical conditions. Observing their lifetimes, decay channels, and formation probabilities allows the refinement of models describing quark interactions and nuclear structure. These rare configurations, though ephemeral, highlight the diversity of matter and the subtleties that emerge when the standard compositions of nuclei are altered. Particle physics experiments often reveal unexpected coherence amidst apparent randomness. In high-energy collisions, cascades of particles emerge that, while individually fleeting, collectively form patterns governed by symmetry principles and conservation laws. Angular distributions, energy correlations, and decay sequences conform statistically to predictions, illustrating that the underlying order persists even within chaotic processes. Recognizing these patterns reinforces the notion that the universe's subatomic architecture, though invisible, operates with consistent, measurable regularity. Cosmic evolution remains intertwined with the minutiae of particle interactions. Supernovae, neutron star mergers, and the synthesis of heavy elements rely upon nuclear reactions dictated by subatomic principles. Neutrinos emitted in these processes escape dense stellar cores, carrying information about the inner workings of these cataclysms. The decay of unstable isotopes contributes energy over extended periods, influencing planetary differentiation and chemical evolution. Each process demonstrates that even the most remote astrophysical events are guided by rules established at scales far smaller than atoms, connecting the invisible to the observable. High-precision spectroscopy bridges the gap between subatomic behavior and measurable phenomena. The energy levels within atoms, influenced by electron interactions, spin-orbit coupling, and quantum electrodynamic corrections, provide exacting tests of theory. Discrepancies between observed spectra and calculated values highlight subtle effects such as vacuum polarization or higher-order corrections, offering insight into both fundamental constants and the structure of matter. Through meticulous measurement, researchers link the properties of individual particles to macroscopic observations, affirming that the subatomic world dictates the behavior of the familiar. Across all domains, from the detection of ephemeral resonances to the modeling of cosmic structures, the universe beyond atoms reveals unbroken continuity. Particles, fields, and forces interact according to consistent principles, producing outcomes that scale from the quantum to the cosmic. The meticulous study of these interactions illuminates the elegant structure underlying matter, energy, and space. Even phenomena that remain undetectable, inferred only through their gravitational or subtle quantum effects, play integral roles in shaping the cosmos, underscoring the profound interconnectedness of the invisible and the observable. Rare particle processes reveal some of the most delicate aspects of the subatomic realm. Events such as neutrinoless, double beta decay, or proton decay, if observed, would illuminate mechanisms that transcend conventional particle physics. Though exceptionally difficult to detect, experiments searching for these phenomena employ massive detectors, deep underground shielding, and extreme sensitivity to isolate minute signals from background noise. Each null result, carefully recorded and analyzed, constrains theoretical models and refines our understanding of symmetry, conservation, and the potential pathways through which matter might transform under rare conditions. Subtle field effects continue to shape observable phenomena. Quantum, electrodynamic corrections, vacuum polarization, and the interactions of virtual particles modify measurable quantities such as atomic energy levels and magnetic moments. The precision with which these effects are predicted and observed demonstrates the extraordinary consistency of physical laws and how minute fluctuations in fields ripple outward, influencing both the stability and reactivity of matter. In this continuous exchange, the subatomic landscape acts as a living framework, where the imperceptible orchestrates outcomes visible on macroscopic scales. High-energy astrophysical environments provide natural laboratories for subatomic physics. In neutron star cores, quarks may deconfine under extreme density, forming phases of matter not reproducible on Earth. Supernovae emit neutrinos, gamma rays, and cosmic rays, each carrying information about the extreme conditions within collapsing stars. Observing these emissions and comparing them with laboratory experiments enhances understanding of how subatomic interactions govern energy release, particle creation, and the synthesis of elements. Across the vastness of space, the same principles that regulate particle behavior in colliders operate to sculpt galaxies, stars, and planetary systems. Precision measurements continue to uncover the interplay between forces. The fine structure constant, the ratios of particle masses, and coupling constants reflect the underlying symmetries of nature. Slight variations in these values would dramatically alter the behavior of matter, nuclear reactions, and stellar processes. That they remain consistent across space and time attests to a remarkable universality, a coherence that binds the subatomic world to the cosmic order. By studying these parameters, scientists trace the delicate balance that allows matter to exist in stable, complex forms, capable of supporting chemical diversity and ultimately life. Exotic states of matter, while ephemeral, reveal pathways of energy distribution and particle interaction. Short-lived baryons, mesons, and quark-gluon arrangements offer insight into the dynamics of confinement, decay, and interaction strengths. Each transient formation contributes to a broader understanding of how fundamental forces govern stability, transformation, and the emergence of structure. Observing these states requires both rapid detection and precise reconstruction, demonstrating the intricate choreography of creation and decay that occurs continuously beyond atoms. Neutrinos, in their subtlety, exemplify the interplay between invisibility and influence. Their oscillations and minimal interaction with matter allow them to traverse immense distances, carrying unaltered information from the most extreme environments. Solar neutrinos provide insight into fusion processes within stars, while neutrinos from distant supernova or active galactic nuclei convey conditions inaccessible to light. These particles, almost ghost-like in their passage, connect the subatomic domain with the behavior of stars and galaxies, revealing that even the most elusive components contribute to the universe's evolution. The vacuum itself participates in the orchestration of matter. Temporary fluctuations generate forces and influence interactions in ways measurable through atomic spectroscopy and high-precision experiments. Casimir forces, Lamb shifts, and other subtle effects testify to a dynamic, active background where energy and fields continuously interact. Space, in this sense, is not empty but a medium of latent activity, a substrate through which particles communicate, forces propagate, and energy transforms. The invisible framework of the vacuum supports the very existence of the tangible world. Across every scale, from fleeting particle resonances to galactic dynamics, continuity prevails. Forces interact, particles decay and recombine, and energy flows according to universal principles. Each interaction, no matter how small or ephemeral, contributes to the evolution of matter, the structure of stars, and the composition of planets. The principles observed in laboratories, reinforced by cosmic evidence, demonstrate a universe whose foundation is precise, consistent, and interconnected, where the realm beyond atoms dictates the behavior of the familiar, shaping reality from the ground up. As one reflects on the subatomic world, a sense of calm emerges. Invisible, intricate, and dynamic, this domain governs every aspect of matter and energy, yet it does so without spectacle or fanfare. The processes are constant, precise, and harmonious, creating the conditions that allow stars to shine, planets to form, and life to exist. Understanding these phenomena offers not just knowledge, but an appreciation of the quiet, profound order that underlies the universe. Each particle, each fluctuation, each field contributes to a continuous, seamless dance that spans scales and epochs, revealing the intricate architecture of reality itself. In this stillness, it becomes evident that the universe beyond atoms is neither chaotic nor arbitrary. Every interaction is a thread woven into the broader tapestry of existence, every decay and transformation a note in an endless, intricate symphony. By observing, measuring, and reflecting upon these processes, one perceives the elegance and consistency of the laws governing all matter and energy. The subatomic world, though invisible and fleeting, is fundamental, shaping the cosmos with quiet precision and reminding us that the structure of reality, in all its complexity, emerges naturally from the simple, unbroken principles of the unseen.